All right, now we want to discuss something called electromagnetic waves. So we had a section a while ago where we talked about the different models of light. And we talked about the wave model. And we had to learn about the wave model, or the wave model was developed because light acts like a wave. You recall that we had the double slit experiment where we shined light through the double slits. And if light was just made out of particles, we get a spot here and a spot here, let's say. But what happened is we get this interference pattern, remember? And so the fact that we got an interference pattern with a double slit experiment proves beyond a doubt, be careful you say that light sometimes acts like a wave. All right, so we want to talk more about this. Light acting like a wave. Now, what's a wave? A wave is a disturbance of a medium. We learned about that a long time ago. So, what's the medium for a rope wave? Well, a rope, What's the medium for a sound wave? Air, right? Air. If we were on the moon, you couldn't hear me. What a blessing, just kidding. Okay, what's the medium for a seismic wave? The earth, right? The earth. What's the medium for a water wave? The water, All right, now here's the question. What is the medium for a light wave? Now, don't forget, what is between, okay, let's say we go to the outer atmosphere of the sun and the outer atmosphere of the earth. What's here? Basically nothing, right? It's almost a perfect vacuum. It's like nothing. But come on, light travels from the sun to the earth. And light is a wave. A wave is a disturbance of a medium. What's the medium? There's nothing there. It's a vacuum, or close enough, So what's the medium, So that's a question that really perplexed people for a long, long time. And let's talk about the resolution of it, okay? All right, but that's the question, right? What's the medium? Because that light travels, right? And light's a disturbance of a medium. There's no medium, right? But you got to be careful. There's no material medium, right? This is a vacuum. Okay, so there's no material medium. But there's maybe other types of medium. Let's see. Media. All right, let's see. All right, so here's a comb. And let's say, you comb your hair and this thing becomes charged, okay? Have you done that before, like when it's really dry or something like that? Okay, so you have a charged comb and you accelerate it. You wiggle it, all right? Now, let's think of Maxwell and Faraday, okay? So you wiggle this charged object. Well, first of all, it's a charged object. So what does it produce? It produces an electric field. Well, you're wiggling it, so you have a changing electric field. Well, what did we learn just a little bit ago? What does a changing electric field produce? A magnetic field. Now, most likely, because we're going crazy like this, what we're really going to get is a changing magnetic field. All right. And what does a changing magnetic field produce? An electric field. And that's probably going to be changing, right? So what we really have is a changing electric field. And what does a changing electric field produce? Changing B field. And what does that produce? You see, getting tired of this yet? So that produces that, that produces that, that produces that, that produces that. It just keeps going and going and going and going, right? Okay. So, well, there you go. How you like that, right? Cut and paste, right? Okay, so Faraday says changing B field creates E field. Maxwell changing E creates B. So that's what we have, right? You wiggled your charge comb, and we just keep getting it. Changing E, changing B, changing E, changing B, just keeps going on and on and on and on and on, right? So here's the important thing. So these fields, they create, right? And they recreate each other. They create and recreate each other. Now, this is like a disturbance, you know? I mean, you have these electric and magnetic fields, and you have a disturbance through the electric and magnetic fields. And this disturbance, it doesn't travel instantaneously. It travels at a certain speed. Well, how fast? Well, let's look at it. Let's figure out how fast this disturbance in electric and magnetic fields change. By the way, what's a disturbance of a medium? It's a wave. Keep that in the back of your head. Okay, don't worry about the math, okay? I know you haven't seen this, just don't worry about it. But all I want you to understand is what I'm going to show you. Okay, so this is called the wave equation. It's a one-dimensional equation which describes the propagation of a wave, right? This is an equation for the electric field, the propagation of an electric field, but travels as a wave, okay? All right, you don't have to know that. All I want to show you is this. For a wave, this is 1 over the speed of the wave squared. Well, this is a wave equation for the electric field. So what does this have to be? It has to be 1 over the velocity squared, all right? That's the important thing, okay? So basically Maxwell, and I'm just showing you the electric field equation. I could show you the magnetic field equation, but I don't really, it's not necessary, okay? So Maxwell is saying, look, this process where you have a creation and then recreation of electric and magnetic fields, in other words, you have a wave, you have something propagating through electric and magnetic fields. This process will only occur if the speed of this wave, this 1 over v, no, well, let me say it again. This process will only occur if this equals that. All right. Well, let's calculate the v then. I mean, you know, we know what mu naught and epsilon naught are, right? Okay, so let's just, so here, let me just show you. So we're going to do this. So we're going to say that 1 over v squared equals epsilon naught mu naught, all right? So flip them. So therefore v squared equals 1 over epsilon naught mu naught. So therefore v equals that. Well, let's just plug in the numbers, you know, and see what we come up with. So I do it over here, right? So v equals, okay, this is the same thing, right? This is the same thing as saying epsilon naught mu naught to negative 1/2 power, right? Same thing. Okay, so you just plug in the numbers, you know. Here's our good old epsilon naught that we had a long time ago. Here's our mu naught. You put it to the minus 1/2, and you get this, 3 times 10 to the 8th meters per second. Now, what is 3 times 10 to the 8th meters per second? Maybe you know, maybe you don't know, but they know, they knew back then, all right? That's the speed of light, right? 3 times 10 to the 8th meters per second is the speed of light. So what does that mean? That means that light is a disturbance of an electric and magnetic fields. So go back to this picture. So, all right, you know, you have light traveling from the sun to the earth. There's no material, there's no matter out here, right? It's a vacuum. But what do you have? You have electric and magnetic fields. Are they made out of atoms? No, they're non-material, right? A field, it's a force field. It's not made out of matter. So you have electric and magnetic fields in here, and light is a disturbance of those electric and magnetic fields. So that's a super big deal, all right? Super big deal. So All right, so that was his prediction, though, right? Maxwell predicted that from his mathematics, right? That's mathematics, you know? So Maxwell makes this crazy prediction at the time. Well, you know, what do you do in physics? You do the experiments. Well, this is not an easy thing to do, you know? So it took 20 years after he made the prediction until it was verified. It was verified. There was a guy in Germany, Hertz, Heinrich Hertz. You know Hertz, the frequency Hertz? So the same, the Hertz that we use Hertz for frequency, right? Well, that's the guy that figured it out. He accelerated charged particles in his lab, and he noticed that they predicted waves that travel at the speed of light. So, wow! Maxwell's prediction was verified experimentally. Now, the rotten thing was, again, so Maxwell made a prediction, 20 years later it was verified. Maxwell had died already. So Maxwell never lived to see his, premier prediction verified. Kind of stinks, right? Okay, so here's the thing. So this is called the electromagnetic wave theory of light. So every accelerating charged object creates a disturbance in its own electromagnetic field. And what's a disturbance in a medium? It's a wave. A wave. The wave spreads out through the field at 300,000 kilometers per second, speed of light. Light is such an electromagnetic wave. So this is a book I bought a long time ago. It's kind of fun. 5 equations that changed the world. The power and poetry of mathematics. So there's all these physics equations, right? And so let's talk about this one with electricity and magnetism. This is a nice book. I mean, anybody can read it. It's written here. Here's someone who can explain science to the layman. So if you've taken this physics class, you can certainly understand everything in this book. So it's awesome, right? The entropy of the universe, Einstein's equals mc squared, Bernoulli, and gravity. Okay, so this is right from the book, and you'll laugh. I hope you laugh anyway. Okay, on the evening of Maxwell's discovery, he had a date with a young lady he was later to marry. While they were walking in a garden, she remarked about the beauty and wonder of the stars. Whatever. Maxwell asked how she would feel to know that she was walking with the only person in the world who knew what the starlight really was. For it was true. At that time, James Clerk Maxwell was the only person in the world to know that light of any kind is energy-carrying waves of electric and magnetic fields that continually regenerate each other and travel at one fixed speed. There you go. All right. And again, remember, fields are non-material. So the medium, see, that's what was so difficult for physicists at the time. They always had, a material, a material medium, like water, earth, air, something you could touch, right? Something made out of atoms or something like that. And that's why it was so hard with the light, because the medium, not made out of atoms, you can't touch it. It's electric and magnetic fields, right? So that was tough. It was tough to figure that out. But he did it. So it's pretty awesome. Okay, so what do we learn? So we learned that light travels at one speed. So light travels at the speed, that sounds stupid. Light travels at the speed of light. That sounds stupid, right? Whatever. Light travels at 300,000 kilometers per second. And we just write speed of light as lowercase c, okay? So the speed of light, lowercase c. It's just easy. Get sick and tired of writing 300,000 kilometers per second. Okay, so what does it mean? It means that any kind of light travels at 300,000 kilometers per second. Could be visible light, could be infrared, ultraviolet, whatever. All light travels at 300,000 kilometers per second, okay? But wait a second. When we talked about waves, we had this super important equation. I call it the F equals ma of waves, right? it was velocity equals frequency times wavelength. So I said that's really, really an important equation. Now here, the velocity is the speed of light, so I can put a c here. Again, that's true for all types of light. So this is fixed, right? C, is fixed, 300,000 kilometers per second. But what does it say about the frequency and the wavelength? They can be anything as long as the product equals 300,000 kilometers per second, right? So, remember, a wave, it's a periodic wave, so it has a wavelength and a frequency and all that good stuff. So let's look at it. Okay, so this is called the electromagnetic spectrum. It's just, or you could call it the light spectrum. It just displays the different forms of light. Because there's lots of different kinds of light, right? So here you go. So radio waves travel at the speed of light, so they're a form of light. Microwaves, form of light. Infrared, visible, ultraviolet, X-ray, gamma ray. They're all forms of light. They all travel at the speed of light. Now here's what's interesting though. Remember I said that they can have different frequencies and wavelengths as long as the product equals the speed of light, right? So look at, this is just the wavelengths. So like radio waves, they can have really, really long wavelengths, even bigger than the Earth, right? And then it keeps getting smaller and smaller and smaller. Look at visible light, the size of protozoans, UV, molecules, X-ray atoms, gamma rays. Look at this. This is crazy, right? Look at radio wave can be 1,000 meters or more than 1,000 meters. Visible, give me a break, 0.5 times 10 to the minus 6 meters. That's pretty small, right? Gamma rays, 10 to the minus 12, size of a nucleus. So there's a huge range in wavelengths of light. Look at the frequency. So, if you have your charged comb, how many times you can wiggle it in a second? Well, good luck, right? If you can wiggle a charged comb 10,000 times in a second, you can make a radio wave. If you want to make visible light, sorry, good luck. 10 to the 15th times in a second. If you can do that, you're wonderful. Gamma rays, 10 to the 20th. Look at the energy. So radio waves, 10 to the minus, okay, this is electron volts. Remember we talked about electron volts? So that's really, really, really small, right? So radio waves, 10 to the minus 10 electron volts. What's that? Nothing. And it better be that way, right? Because, if radio waves had a lot of energy, here we are in this room or wherever you are, and there's probably radio waves going in your room, right? Because you can just turn on a radio, right? But think about it. If the radio waves had a lot of energy, you'd probably be dead, right? Because they would kill you. Okay, so super, super low energy. Visible, 4 electron volts, nothing. Gamma rays, 10 to the 6th, 1,000,000 electron volts. That's why gamma rays are used to kill cancer cells. So all I'm saying is there's all this huge range in wavelengths, in frequencies, and in energies. Okay, I like this slide a lot. So same as before, but just different. That makes a lot of sense, right? Same information, but just portrayed differently. So here's the electromagnetic spectrum, right? Radio, microwave, infrared, visible, UV, X-ray, gamma rays. But look, and by the way, it doesn't stop here. It keeps going over here, keeps going over there, So if you think of the entire spectrum of light, how much does visible light make up of? How much of the entire spectrum is visible light? This much, right? From over here to over here, visible is this much. Not very much. So, think about it. If you're an astronomer and you're looking at the outer space, and all you're using is visible light, you're missing almost everything, right? All you can see is this. You can't see anything over here. You can't see anything over here. So you're missing the boat, Okay, so what have astronomers done about that? So astronomers, what they've done, they recognize the limitations of this. So astronomers have built like radio telescopes, microwave, like satellites, cameras, infrared cameras, ultraviolet, X-ray, gamma rays. So astronomers, what they're trying to do is they're trying to look at, you know, the universe in every single, or nearly every single kind of wavelength. Because when they do that, they learn a lot of things, you know. You're not going to see everything if you just look into that, the visible. You'll learn different things when you look at different wavelengths. So that's kind of a big revolution in astronomy, developing all these different satellites and telescopes in different wavelengths. So here's just an example. This is Orion. So this is V for visible. Okay, so this is the night sky, and there's Orion. And this is the star map. So it's kind of boring, you know? You just see the, you know, a few stars. But then this is ultraviolet. And if you're used to just seeing that, and you see that, and you're an astronomer, you get all excited, right? Because what's all this stuff going on, you know? Why? I mean, you just expected 1, 2, 3, and a few here, you know, and maybe some here, but why is it so incredibly bright in ultraviolet? I mean, what is going on here, you know? Then you look at infrared, and it blows your mind. What is going on here? And so all I'm saying is that as astronomers have developed these telescopes and satellites and they're able to see different wavelengths, they've just learned, or they've discovered things they never even dreamed of. And again, it's just because their vision is expanded, right? So it's quite amazing. Okay, not yet. Okay, so I will put a link on Canvas for like a 7-minute video clip. So, I don't know, 10 or something years ago, there was a camera built. It's called Spitzer, that's acronym for something. And all it did was detect infrared light. And they use that because it's easy to discover planets orbiting other stars using infrared light. And anyway, it's just a really cool video. I didn't want to spend the time now to show it to you, but I'll put the link on these slides. Because, you know, all these PowerPoint slides are on Canvas. I hope you know that. So I'll put the link on Canvas, and you should just watch it. It's really, really cool. All right, let's quit.